Good evening, everybody. Hope you're all doing okay on this Thursday evening. So tonight we're going to be talking about lipids. See here, some other interesting biological molecules. Pretty much each day from here on out, we're going to talk about a different category of biological molecules. So we looked at carbohydrates on Tuesday. We're going to look at lipids today, and then next week Tuesday is proteins, and then Thursday is molecular genetics, DNA and RNA. Hey, Alyssa. Hi, Daisy. Hey, Joey. Good to have you all this evening. All right, let's get started. So, we talked about carbohydrates on Tuesday. Hey, Jennifer. Those were a class of molecules that were all built from the same types of structures. You had these monosaccharide building blocks, and then that would build them up into these bigger molecules. Daisy, sorry, I don't think I got anything from you on Discord. Let me check. Oh. Oh, to fix the mastering chemistry. Yes. I didn't see that. It didn't come up before, but I see it now. And then there's another message just saying, did I see that other message? So no, I did not see that message, but I see it now, and I will fix that. Yeah, I think one of those assignments is wrong. At least one of those is wrong on Blackboard. So sorry about that. All right, so back to lipids. What I was saying was the carbohydrates are, you have this like structural basic building block, and then everything else comes from those things being linked together, or slight variations of those original molecules. We're going to see the same thing with amino acids and proteins next week. You've got these amino acids, they have some slight variation, and then everything else is built up from there. Lipids are different. Lipids are a much broader class of molecules. It's not just one type of structure. Lipids applies to pretty much everything that is nonpolar or mostly nonpolar in the body. And sometimes the word that's used for that is hydrophobic. So hydro like water. Hydrophobic would be things that are nonpolar, so not mixing with water. The opposite of that would be hydrophilic, which are the things that are mixing with water. So the carbohydrates we saw on Tuesday are very hydrophilic generally. They have lots of OH, can do that hydrogen bonding just like the water. Lipids being hydrophobic, now we're talking about nonpolar things that can't mix with water as much. And so that means we're going to see lots of different structures today. They all are classified as lipids, but they'll have their own names as well within that category. So we'll start with the fatty acids. So fatty acids look like this big molecule that you see behind me. They are a bunch of carbon and hydrogen, generally 11 to 19 carbons in length. And then, actually, they get into the 20s, I believe, too, sometimes. And they're often referred to as having a head and a tail. So the head is the carboxylic acid group. That's where it gets the name fatty acid. That's a carboxylic acid functional group. And then the tail is the nonpolar part. All right, so fatty acids are really both polar and nonpolar. They're sometimes known as amphiphilic, like both. They want both things, but they're that's why this separation of polar and nonpolar is kind of not an absolute distinction. It's more like some parts of molecules can be polar and some parts of molecules can be nonpolar, and that's more important than what is the overall molecule. So in a fatty acid, you've got the nonpolar tail and you've got the polar head. And often those carboxylic acids are deprotonated, so the hydrogen is removed in an acid-base reaction. So a base could pull that hydrogen off. And then you'd have a carboxylate like palmitate. So if you have, These molecules are often used as soaps because the nonpolar tails can dissolve greases and oils, and the polar heads can dissolve in water. So um, if you look at soaps and shampoos and the ingredients, you might see things like palmitates, oleate, things like that, and that refers to these fatty acid molecules that are helping to dissolve those oils. All right, so now we see a variation on this palmitic acid up here. Notice a lot of these molecules have their own names based on what they come from. So palmitic acid comes from palm oil, or is a big part of palm oil. So that's where that name comes from. It's not really a chemical name. You don't have to know these specific fatty acid names. Um, so if we then go to palmitoleic acid, you can see the difference here, that it now has an alkene functional group. So let's add that there. There's now an alkene functional group here. And this is going to be a little tricky, but let's do this. Let's draw the condensed formulas for each of these molecules, and we can do it in a couple different ways. So we'll just go up here. We don't have to do it exactly down there where it says. So let's go back up to palmitic acid. If we were to draw a condensed structure for this, it might look something like this. We have to figure out how many carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons total. We've got a CH3 at the end, so we'll start there. And then we could write, what did we say? I already lost that number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we could write 14 CH2s right after that CH3. So CH2, 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 14 times. But I don't want to do that. Let's shorten that up a little bit. Let's use parentheses and say there's 14 CH2s. Now, because of what we know about condensed formulas and about carbon in general, we know that that doesn't mean 14 CH2s all coming off of this CH3, because that wouldn't make sense chemically. Carbon has to have 4 bonds. So we can assume that there's 14 CH2s after the CH3. And then finally, the functional group, a carboxylic acid functional group in a condensed formula is written one of two ways, either CO2H, or sometimes that is written as COOH. So you'll see it both ways. So that's how we'd write a condensed formula for palmitic acid. All right, so now if we want to do palmitoleic acid, we can't take quite as much of a shortcut there because of this double bond. So we have to go CH3, and then we've got 1, 2, 3, 4, 5 CH2s. Then we've got a CH double bonded to another CH. So in a condensed formula, you could just write this CH, but just to be clear, it's not that hard to add the double bond there, and just to make it really obvious. Remember, when we write condensed structures, you don't have to condense it all the way down. You can still add bonds in between, if in between the carbons or the CH whatevers, if you want to make it a little clearer how things are connected. All right, so CH, and then on the other side of the double bond, 1, 2, 3, 4, 5, 6, 7 more CH2s. And then finally the CO2H. All right, so now we're going to use another term that I can't remember if we used when we talked about hydrocarbons or not, but it's saturated and unsaturated. And those words describe if the molecule has as much hydrogen as possible. So a saturated alkane would be something like CH4 or C2H6 or C3H8. So in other words, you have a certain number of carbons, and then you have all of the hydrogens that you could possibly put on there. That's called saturated. When we added things like double bonds and triple bonds, we talked about those as, I don't remember if we talked about them or not, but they are sites of unsaturation. There are ways to reduce the number of hydrogen on that molecule. Now, when it comes to fatty acids, we use those same terms, saturated versus unsaturated, and we're only talking about that tail in this case. So we realize that the head of all fatty acids is technically unsaturated because it has some double bonds and other stuff there. But the tail, if the tail doesn't have any double bonds in it, that's known as a saturated fatty acid. And if it does have a double bond in it, then it's known as an unsaturated fatty acid. So in most naturally occurring fatty acids, if they have a double bond, the double bond is in this particular geometry called cis, which means that basically the hydrogens are on the same side of the double bond. If we imagine like a line going through it like that, the hydrogens on the same side. Sometimes people prefer to think of it as the other things are on the same side, but that's known as a cis double bond. And most naturally occurring unsaturated fatty acids have cis double bonds like this. And because double bonds don't rotate, that kind of locks this fatty acid in this geometry. It makes it kind of turn this corner. And so because of that, you can probably figure this out if you're going through the questions here. These unsaturated fats cannot pack quite as tightly as the saturated fats. So these saturated fats, if you go back thinking about the dispersion forces that we looked at several chapters ago now, we said that the better overlap you can have, the closer the interaction and the more surface area, the higher the stronger the intermolecular forces. And that's true with these as well. So these nice straight saturated fats can pack quite nicely and can really have strong intermolecular forces, whereas the unsaturated fats kind of don't line up quite as nicely. So they're a little bit they have a little bit weaker intermolecular forces. The consequence of all that is that saturated fats will generally have higher melting points than unsaturated fats. So when you think of fats that are solid at room temperature, so you think of like animal fats, things like butter, and then some plant-based fats like coconut oil or shortening or palm oil that are solid at room temperature or close to room temperature. Those are primarily saturated fats, so they're primarily made of these types of acids. And then you think about the fats that are liquids at room temperature, the oils, canola oil, olive oil, things like that. Those are going to be more unsaturated, made of more unsaturated fats. And you can calculate this stuff out if you want. You'll notice there's no place to put to turn these in this week. I figured we've done enough of that. A lot of these types of things are more just telling you about the molecules, so actually practicing the skills isn't quite as important as in some of those earlier chapters. I do encourage you to work through them, but I'm not going to collect and grade these. So just to compare, you can see some different related acids. And we should note here, I didn't draw these, but these double bonds should be cis double bonds. So they should also have that kind of like branching, curving structure. And the more double bonds you get, you actually kind of start to get it going like in that kind of a shape as these curve around each other. So if you look up the structures of linoleic acid or linolenic acid, which I believe are found in like lanolin, like sheep fat and stuff like that, you'll see some of that. I could be making that last part up. I don't remember for sure. But you can see that as you add more units of unsaturation in the fats, the melting point goes down. So something like stearic acid with a melting point of 69 degrees C is a solid at room temperature, but oleic acid and these others are liquids at room temperature, and something like linolenic acid won't solidify until you get actually way down below freezing. All right, so the other distinction then, besides just saturated and unsaturated, is we can talk about monounsaturated versus polyunsaturated. And you can probably figure out what that means. But monounsaturated is just one unit of unsaturation, so one double bond like oleic acid. And polyunsaturated fats are ones with multiple double bonds in them. So things like linoleic acid, linolenic acid, those kinds of things. All right. So some more just brief nomenclature that you might want to know. If you've heard of omega-3 or omega-6 fatty acids, omega-5 fatty acids, things like that, if we go back to these chains, that has to do with counting where the units of unsaturation are from the end. So generally in a molecule, the most important functional group, that carbon is known as alpha. So alpha is the beginning of the chain. So in this case, the carbon next to the carboxylic acid is the alpha carbon because it's right next to the functional group. And so alpha, and you can count the rest of these based on the Greek alphabet, but generally we only refer to like alpha, beta, maybe gamma coming from there. But then omega is the last letter of the Greek alphabet, so the end of the chain, the other end of the chain, is known as the omega end of the chain. So like the end. If this is the beginning, then this is the end. And so an omega-3 fatty acid is one where the double bond starts 3 carbons in from the end, from the omega carbon. So this would be 1, 2, 3. So linolenic acid would be an example of a 3, 4, 5, 6. So a 3, 6 omega-3, 6 fatty acid. And then this one would be 1, 2, 3, 4, 5, 6. So linoleic acid would be more like an omega-6 fatty acid. And the reason those are important is, like you've heard of that they're important to eat and things like that. Other enzymes take those molecules, and if those double bonds are in the right position, it makes them able to be processed into things like prostaglandins and some hormones and other important biological molecules. So you need some source of those fatty acids so that your body can process those into those things that it needs. All right, I think that was all I was going to say about that. Yeah, okay. All right, so from fatty acids now we can build up some other types of common lipids. One is waxes. Waxes are esters of fatty acids. So remember back last week when we looked at esterification reactions last Tuesday. We talked about dehydration, condensation, esterification. All those words mean the same thing in this case. We got a fatty acid this time as our carboxylic acid. So it's same thing. It just has a much longer chain. And we're going to react that with some sort of long chain alcohol. So again, 18 carbons here. But that's why, like, when we looked at these reactions, we used those R's because R could be whatever. Having some big long chain doesn't affect the actual reaction part where the OH and the H are going to end up together and the carbon's going to connect to the oxygen. That's the exact same as we did with those smaller molecules last week. Now that they have these really big chains, we form what we call a wax. And so the wax is an ester made of a fatty acid and a long chain alcohol. And waxes are used in the body for various things, like the example up here, earwax as a protection from foreign bodies. I think there's some other waxes around in the body, and then there's lots of plant waxes that are made similarly. So this is a carnauba wax, which comes from a leaf, I believe, or some sort of a plant, and is used. This is like used for car wax and stuff like that, and lots of other waxy things. But you can see it's a really, really long chain. And by making this an ester, yes, there's still a little oxygen here, but now this molecule is almost entirely nonpolar. So it's a very, very long nonpolar molecule that also burns. So it's very another thing that you probably know about fats is they store energy in a pretty efficient way. Carbon-carbon bonds and carbon-hydrogen bonds are very have a lot of potential energy. And so when those things burn, they can release those energies. So these are very efficient sources of a great deal of energy, and that's why we see waxes and things like candles and so forth. All right. And then we get to triglycerides, which again looks a little tricky. And we did this when we talked about esterification last week. Question, is the process of dehydration the same? Yes. So you can dehydrate those as well. Or I'm sorry. The process of dehydration is the same. Yes. So you would group the OH and the H to form water, and then group the OH and the H to form water, and then you connect the rest of it. I was going to say, I thought you were asking hydrolysis, the opposite direction, and there is a possibility of that too. You can hydrolyze these things apart in some cases, although sometimes when the waxes get big enough, they actually prevent those water molecules from getting in to do the hydrolysis. But in certain conditions, high temperatures, acid, stuff like that, you still can, strong base, you still can hydrolyze them as well. All right, so if we do that same process, we take fatty acid, but don't get too scared off by all of the molecules here. We're just taking a fatty acid and reacting with an alcohol again. So same type of dehydration or condensation reaction, same thing. But this time the alcohol is glycerol. Glycerol is a 3-carbon molecule, so this is CH2, CH, and CH2 here, if that wasn't clear. A 3-carbon molecule with 3 OHs. It's also known as glycerin. That's the same molecule. So glycerol can react with fatty acids, or really any carboxylic acids, right? Because we can do hydrolysis. And condensation or dehydration. Can do dehydration. Yeah, and I left you this to do this before. It's actually the backwards reaction of this. So when this all comes together, you dehydrate here, dehydrate here, dehydrate here, and you end up with a triglyceride. So you have 3 fatty acids that are condensed or dehydrated onto glycerol, and that gives you a triglyceride. You can do the opposite reaction as well, and you can hydrolyze a triglyceride back into its fatty acids and glycerol. And a similar, or a process that is almost like that is used to make biodiesel, the fuel that you can use interchangeably with diesel fuel. You can take a triglyceride like a plant oil, and you can break it apart. You can hydrolyze it into fatty acids and glycerol, and you add kind of one more thing to help the fatty acids behave the way you want them, and you have this fuel. But yes, this is the same thing. You can also, it's not shown here, you may also have heard of monoglycerides or diglycerides. And as you might expect, a monoglyceride just has one fatty acid connected, so then the other 2 would still be OHs. A diglyceride would have 2 connected and 1 OH, and then the triglyceride has all 3. All right. And the general the general more chemical term for that is triacylglycerol. So you may see that term, but more commonly they're known as triglycerides. In this example, all of the fatty acids are the same, but they don't have to be. In fact, many common triglycerides are made of multiple different fatty acids. So maybe there will be one saturated and a couple unsaturated, or some different unsaturated ones, or different carbon lengths. There, you can imagine there's a huge possibility of combinations there. Another interesting thing about this, if you try to kind of draw this out, you'll notice that we had to really distort the bond angles here to get this to fit on the page properly. So we made this right angles, which we know are not really right. They'd be, zigzagged the way that we've been drawing all these things. And then we kind of use the condensed structures to shorten this up a little bit. This bond angle also looks weird. If you try to draw it out with the correct bond angles, it doesn't quite work. And that's true in real life as well, that the chains don't all kind of hang down in one direction, that a triglyceride really often looks more like, there's a couple different ways that it can arrange itself. So it can go, if here's our 3 carbons, a triglyceride can go kind of like this, which is known sometimes as a tuning fork configuration. So you have your glycerol here, and then your oxygens here and here, and so you have 2 chains going out one way, one chain going out the back, and then those units can pack to make whatever fats you want to make. This is how it's arranged in, for example, cocoa butter. If you've ever worked with chocolate, you have to do a process called tempering. You have to keep the chocolate at really precise temperature control, because otherwise those cocoa fats will not arrange themselves in the right way, and you'll get the wrong packing structure, the wrong solid structure of those molecules. And that's what happens if you try to just like take some decent chocolate and melt it to make candy. It doesn't quite work out. It often gets kind of a hazy color and kind of crumbly and melts really easily. It doesn't have that nice shiny look and the snap to it. And that's because you have to go through this process of keeping it at exactly the right temperature to get those fat molecules to pack properly, those triglycerides to pack properly. That's also what happens, by the way, if you leave chocolate out for a long time. It gets kind of like a haze on the surface. That's not mold or anything. It's still perfectly safe to eat. It's the triglycerides rearranging themselves into a different type of a structure. All right. So another interesting thing that happens is there's a process called, so we talked about condensation, we talked about hydrolysis. That was sort of forwards and backwards. There's another reaction that's done to unsaturated fats called hydrogenation. And hydrogenation, unlike hydration would be adding water, hydrogenation is adding hydrogen. So you could take something like linoleic acid and you can hydrogenate it to form oleic acid. Look what's happening here. We have a double bond here, so CH. And then after hydrogenation, that's become CH2. So we've added hydrogens there. And then you also, hydrogenation is sometimes a hard to control reaction. You react with a bunch of alkenes and add hydrogen to them. So you also form stearic acid, which is a totally saturated fat. So when you have hydrogenated oils, often mimic saturated fats, because that's what they are. So vegetable shortening, for example, like Crisco, stuff like that, you take unsaturated plant-based oils, you hydrogenate them, and basically make them into saturated fats, and that's what shortening is. Now, a byproduct of that process is something like this, where you don't actually get rid of the double bond. You just kind of flip it. So instead of being this cis double bond, it's now a trans double bond. It's going, see how the hydrogens are on the same side here, and then here they're on opposite sides. So yeah, good question. Where did the H go? Well, it's a line structure, right? So we don't draw in all the H's, but let's draw them in so we can see. So these are drawn in, those are drawn in. Then when it's hydrogenated, these same carbons have extra hydrogens, because every carbon needs 4 bonds. So if those were our 2 carbons right here, we added hydrogens to those. And then over here, we basically did the same thing. So 1, 2, 3, 4, 5, 6, 7, 8, I think here is where the new ones would be going. And it would kind of stretch out because single bonds can rotate. So now we can stretch it out into a nice thing like that. So what happens sometimes in this hydrogenation process is you form the trans isomer. So instead of the cis isomer, you get the trans isomer, and this is what's known as trans fats. You may have heard about those. They were popular for a long time until there was significant evidence that they're actually far worse for you than even any other saturated fats or anything like that. And so they're now, the FDA has worked in the last 10 or 20 years to really get trans fats completely off the market. And so you won't see a lot of trans fats anymore. One big advantage to trans fats is that they extend the shelf life of whatever you're making with them long time. So a lot of if you've heard of things like Twinkies last forever, a lot of that came from the fact that they could stay in a vending machine for a really long time without degrading because of the trans fats. We don't really use trans fats anymore, so it's not so much of an issue. If you see in your ingredients partially hydrogenated something or other, like partially hydrogenated soybean oil, that is talking about trans fats. But in most cases now, there's such a small percentage of what you're actually eating that it's not too big of a deal. You know, it's not something you have to avoid every possible thing of. It's just something that is generally worse for you. So the bottom one here, this L Leidic acid is the trans one. And where that, yeah, the last one, where that comes from, again, if we draw kind of like a parallel line to the double bond in these cases, look at the position of the hydrogens relative to the line on these two. So in this case, you can see the hydrogens are both on the same side of the line, whereas here they're clearly on opposite sides of the line. So trans means opposite, and cis means same. So same side, opposite side. The other reason trans fats became so popular is back when, let's say, 70s or so, 70s and early 80s, saturated fat was like the evil thing that you shouldn't eat. You know, every so often something trendy comes up. I think now it's probably like carbs, something that people just say, oh, you shouldn't eat that. It's really bad for you. You should avoid that. And so saturated fats were really like nobody wanted to eat saturated fats. So what they could do is they could make trans fats, which are technically unsaturated fats because they have a double bond, even though they behave like saturated fats. So they could have something that's full of trans fats, but label it no saturated fat, and people would go, "Oh, good, it doesn't have saturated fat. It must be fine." It's not fine, and now we don't really use them anymore. All right, let's look at some other types of lipids besides the fats. So another important class is the phospholipids. So phospholipids or glycerophospholipids are similar to the triglycerides that we talked about, but they now contain some charged groups that make the heads even more hydro hydrophilic. So we've got phosphate here, and then some nitrogen as well, and then you've got this big tail as usual. And this is important. We'll get to the steroids in a second. I just want to show the picture down here. This is really important in cell membranes. So cell membrane, this is a cell membrane here. And the blue little spheres with the tails are those phospholipids. So the blue part is the polar head, the phospho part. And then the squiggly lines here are the fatty acid parts, the hydrophobic fatty acid parts. And there's a layer of two of them, so here and here, because of the outside here is going to be a water-based something in your body, and then the inside, the intracellular fluid, is also water-based. So the polar heads are pointing toward those water areas, and then there's this non-polar layer that protects the cell, and this is known as the phospholipid bilayer. And so this allows the cell to somewhat control what types of molecules can come in and what types can't. And there's a whole, if you go on and take more biochem, you'll learn all about the transport and how we get stuff in there. If you do anything with drug design or medicinal chemistry, that's a big part of designing new drugs. It's not just enough that they do the thing they're supposed to do, like interfere with a virus or something like that. They have to be able to get into the cell through that phospholipid bilayer. So there's all kinds of research on what types of molecules can do that and how to get them through that bilayer. And it's a tricky problem because you have a polar outside and you have a non-polar inside. So stuff has to be polar enough to get through the bloodstream and then also non-polar enough to get through that phospholipid bilayer. And that poses kind of a tricky problem for a lot of molecule design. But again, those phospholipids are made from those fatty acids. So another reason why we often have to have fats in our diets, although I think some of these we can make also. Some of them are essential, which means we can't make them, we have to eat them, and others are inessential, which means we can make them. All right, and then I think the last couple components of the lipid family that we can talk about are the steroids. So steroids in general are molecules that have this type of a structure. They generally have a pretty recognizable 4-ring structure. You can see the 4 rings here. 1, 2, 3, 4, 1, 2, 3, 4. Those steroids, like cholesterol, play an important part in the in that lipid bilayer. And then also we have hormones that end up being made from those sorts of things. So part of having those essential fats is that our body can make these types of molecules from them. And many of the steroids have that kind of structure. Steroids in general are considered part of the lipids, even though they don't look anything like the fatty acids. They don't have the chains. They're not quite as obviously non-polar, but they are still in that lipid category. One interesting thing that you should be able to do now is to look at these molecules and pick out some of the functional groups. So you'll notice cholesterol is mostly non-polar, so we've got mostly just alkane type functionality. There's an alkene at the bottom, and then there's one little alcohol here. And then we've got some hormones here, estrogen and testosterone, which you'll notice have some other functionality. Estrogen having an aromatic ring here. This is this benzene ring, the 3 alternating double bonds. Testosterone having a ketone. So a lot of those biological molecules that you may have heard that end in -one are ketones and have ketone functional groups there. Then you can see the cholesterol in here. Yeah, here's the cholesterol here with its OH poking out. And that helps to adjust the fluidity of that cell, how much stuff can get in and out of that phospholipid bilayer. And then there's some questions here that you can answer about things that you would expect lipids to be able to do in the body. So to sum up, lipids are the primarily nonpolar parts of the molecules in the body, the biological molecules. It's important to know about the fatty acids, what they look like, that they have this head and the tail, and the head is a carboxylic acid, and the tail is a long carbon chain. There can be units of unsaturation in that chain, making it an unsaturated fat, mono or polyunsaturated. We can refer to the position of the double bond based on the proximity to the tail using omega and a number. And then we can link those fatty acids either with alcohols to make waxes or glycerol to make glycerides. And those can be mono, di, and triglycerides. And then we can have phospholipids in there as well. Phosphoglycerides, right? Is that what we call them? Glycerophospholipids, which, and the key to look for those kinds of things is the phosphate here. So what you'll be responsible for in this chapter is first recognizing different types of molecules. So is this a fatty acid? Is this a triglyceride? Is this a glycerophospholipid? Is this a steroid? Things like that. Also putting them together using those condensation reactions and taking them apart using hydrolysis. Nothing new there. Those ideas, condensation or dehydration, where we remove water and connect what's left. We did that in the carbohydrate chapter as well. And then hydrolysis, which is the opposite, adding water and breaking apart on those bonds. So are there questions? Are there other things you want to talk about with regard to lipids or anything else? We can talk about the final, sure. So the final is, I'm not sure how the timing is going to work on the final yet. Next week is our last full week of regular class, and then there's finals week after that. Because of us being remote, my plan is to have a fairly long time for you to choose to take that final. It is a standardized final, so all of the Chem 100 sections are taking the same exam that is mostly multiple choice with some numerical calculation type answers. Um, it will be a comprehensive overview of the entire course. It will not be primarily the last section of the course. It will be everything all together. I don't know if we really broke it down by topic and percentage. I don't know if it's exactly equal with everything. I'm sure it's not. But the idea is that it's a full final exam about everything. So you'll see a little bit of everything from the whole semester on there. So there isn't a study guide. There is we can definitely have a live study session of some sort, maybe next week, Friday, or like the Monday of exam week or something like that, Monday or Tuesday. Um, and and we can go through. I think the best study guide is one to make a list of all of those objectives for each unit. So every single folder on Blackboard says like this is what you should be able to do in that unit. So make a big list of all those things. So you can go through and go, okay, can I do that? Can I do that? Can I do that? Can I do that? And then focus on the things that maybe you're not sure you can do. And then also all of the old exams, both the ones you took and the ones from Blackboard, you can kind of go through and pick out questions. I think you'll find, that a lot of the things uh, you won't have to study because it's things that we've been doing over and over again. So, dealing with chemical structures, stuff like that. I think those will be okay. So you can really sort of focus in on the things that are giving you the most trouble, that you need the most practice with, and spend your time working on those. We have two more topics after this one. We have proteins and, well, okay, yes, it's one. It's like one. They're together, but it's proteins and molecular genetics. Proteins, structure of proteins, and then structure of DNA and RNA. So we'll do one on Tuesday and one on Thursday. And they'll be in very much in the same format. There is no quiz this week. There's going to be a quiz next week. It'll be our last quiz on all of the biological molecules together. I think there just isn't enough with just these small topics to do a quiz this week. So we'll do one more quiz on carbohydrates, lipids, proteins, and nucleic acids. We are all finished with labs. I was going to put in another virtual one for this time, but I think everybody just needs time to get studying for the final, finish final papers and projects for other classes. We had enough time in person. We did some other virtual labs. I think that we've done enough in terms of labs this semester. Other questions? If you I guess I should say if you missed some labs and you need to do some makeup work with that, because I know we were planning on that week before Thanksgiving for makeup work and then we couldn't do that. Um, Let me know because we do have other virtual labs. There was a molecular models one from quite a ways back that you can do if you missed a lab. If you've done the labs, there's no need to do extra work. It's not worth extra credit. But if you missed stuff, then you can catch up on that if you need to. And if you haven't turned in some of your lab reports yet, or mastering chemistry, you can still do those as well. So get those done and turn those in. Um, I think the deadline is next week, the end of next week, which is truly like the last day of class before finals week, is when really everything needs to be done. Other questions? I guess I have a question. Can you all access the Blackboard exams, exam 1 and 2, and the mastering chemistry quizzes that you already completed? Can you still get to them for practice? Yeah, exam 1 and 2. So exam 1 was on mastering chemistry. Exam 2 is in Blackboard. Can you still get to them for practice, or do I need to like remove a password or something? Yeah, if somebody can just check whenever and let me know. I think I have stuff set. Exam 2 doesn't show the answers. Okay. Let me see if I can change that. And you can get the mastering chem quizzes. That's good. And you can get exam 1, but not exam 2. Okay. I'll see if I can mess with that and see how I can get it to show you the answers. All right. If that's all, then I will see you Tuesday. Let me know if you have other questions or you can't get to things that you need. I think when my phone updates or something, I stopped getting Discord notifications, so I just have to remember to like open it every now and then so that I can get those. Yeah, because now a bunch of stuff came in. So sorry if I missed your stuff. All right. So thanks everybody, and yeah, I'll see you Tuesday. Happy end of the semester. I hope you don't have too much stuff to do. But I mean that's kind of how it goes. So almost done. Almost done. You can do it. Good night.